let's design a theoretical robot here. So that theoretical robot is going to be on a table. Right? So it's going to be on a table like this, and it's gonna be a hammer. So it's gonna have this little handle that comes out, and it's gonna have this nice this nice business end. What's the business end of a hammer called? I can't remember. Anyways, and it's tied to some sort of motor right at the base that allows you to basically swing this here, and then we'll have a slice of pizza that's just hanging out there, right? It's just hanging out, and there's a camera system, and it detects that if my wife is going to steal my piece of pizza, this hammer will come down, break her fingers, automatically call the cops. I'll end up in prison. It won't be fun. But either way, that's the robot that we've got designed here, the anti-pizza theft device. Anyways, we want to figure out the amount of torque that this motor is going to need, right? How much torque is that motor going to need? So we need to know a little bit about the load, or what's going on with our hammer here. So we're gonna kind of simplify things a little bit here. So we've got the handle part, and let's say that it's let's just say this it's handle is what do we want to do? We'll say 1 Newton per centimeter. So for 1 centimeter of length, it adds 1 Newton to the whole mass here. And let's just say that let's say its dimension is, we'll say 20 centimeters. So therefore, this whole thing weighs 20 newtons. And then I'm going to do another simplification and say that the active end of the hammer is just concentrated right at the end. We might be able to do some sort of offset based on the width of the metal part. But let's just say it's right at the very end of our length. So, and let's say that we weigh that, and that turns out to be just a flat, what do we want to do? 50 newtons. So, here's what we've got. What we really have is the weight of this handle you can actually assume is applied at the center of its handle, since it's evenly distributed. It's 1 Newton all the way across. And so this is 10 cm, right? This is 10 cm. So you know what? Let's make this a little bit more simple here. Let's make this 1 meter. So 1 meter there. So the force that's applied here, right? Or sorry, not the force. We want to figure out the force. Sorry, not torque. So the force that's applied at this point is 20 newtons, right? It's applied right at this center. And at the very end of this length is 50 newtons. So this is right here. This is 0.5 meters. And this here is 1 meter. Now we can figure out both of these, what torque is being applied here, knowing that torque is just a force times a distance. So this torque is 20 newtons times 0.5 meters, or so that is 10 Newton meters. Cool. And then the second one here, this is just 50 newtons times 1 meter, or 50 Newton meters. So that means that the total torque that's being applied here, is 60 Newton meters. And I like to do these examples when they're fully outstretched, meaning gravity is this way, because that makes it the easiest to kind of work with there. Otherwise, you kind of got to do some weird math if it happens to be at an angle. So I like to think of everything as all outstretched. If it was a multi-link arm, I would still take it and outstretch it straight. So 60 Newton meters of torque. This is our final answer right here. 60 Newton meters is what our motor needs to be.